All right. Of course, our thermodynamics things, right? Okay, so this guy is our heat engine. This is our sort of our fundamental thing, right? So if we've got a piston, it's always a piston in a cylinder, right? We have a working gas. We've got this piston, and the piston can move up and it can move down, right? Okay. Heat can flow in. That's positive Q. Heat flows in. Heat could flow out, though. That would be negative Q, right? If the piston moves out, that's positive work. And if the piston moves in, that's negative work, right? And then the temperature of these gases, right? If we look at the temperature of those gases, remember that U is 3 halves nRT, right? Okay. And so, um, and so if the temperature rises, then the U is positive. If the temperature goes down, then the change in U is negative, right? So this is it getting hotter or colder? Hotter is positive and colder is negative, right? Temperature wise, right? Piston moves out, piston moves in. These are negative things, right? Heat flows in, heat flows out, right? So positive things, heat flows in, the thing gets hotter, the piston moves out. These are all positive things. So very simply, if 12 joules flows in, right, and it, let's say the gas absorbs 3 joules, right, then that means that it's got to do. Well, let's see, we got to do the math here. It's got to do 9 joules of work, right? Yeah. So if 12 joules flow in, it's pretty simple. But of course, the piston can move in all different directions, and heat can flow in and flow out, and we can make it a lot more confusing than that, right? And then this is work is P delta V, right? Okay, so if we had a situation where it was isobaric, where the pressure did not change, right? Right, baro, like barometers measure pressure, right? So isobaric means constant pressure, right? Okay, isobaric is constant pressure. Then our work that we do is just force times distance, right? Okay, and then you're like, well, why is that distance? Well, because you think about this, right? Pressure is force over area, right? So force is just pressure times area, right? And then force times distance is work, right? And so pressure times area times distance. Well, if this thing moves some distance, right? Some distance S, then the amount of change of volume really is just that area times the distance the piston moved, right? And that's why it's P is delta V, right? P delta V. So this is an isobaric process, right? And then what are the other ones, right? There is isochoric. It's constant volume. It's not a commonly used term. They just usually just say constant volume, right? Isothermal, right? So by the way, if it's isochoric, work is 0. The piston doesn't move, right? Okay. Isothermal is constant temperature, right? And so our change in U is 0. If the temperature doesn't change, right? The internal energy is 3 halves nRT. If T doesn't change, U doesn't change, okay? So if it's a constant temperature, there's no change in internal energy, right? And then, of course, there's adiabatic, which is a term that's so common that I would think it would be included in the word list for spelling bee, right? I think it should be. Constant heat. Okay, heat flow is 0. Let's just say this. Q is 0. Okay, heat doesn't flow in or out. So adiabatic processes are either well insulated or more commonly, they just happen really fast. Heat flow takes a long time. So if you just compress that thing really quickly, and that's the demonstration where you slam that piston down and you can ignite, a little bit of cotton fibers. It's kind of cool. And this is how diesel engines, of course, ignite the diesel fuel. They just have a huge compression ratio. The temperature goes way above the kindling point of diesel fuel, right? And then you just shoot some diesel fuel in there and it explodes, right? So adiabatic is no heat flow, okay? And so you look at these processes, right? This would be adiabatic. This would be 0. Okay, isochoric. This would be 0. And then isothermal. This guy's 0. Isochoric. This guy's 0. Adiabatic. That guy's 0. Right. This is our change in internal energy, so you can calculate that. Here it is in terms of normal things. Here it is in terms of the number of particles in Boltzmann's constant. Right? This is our entropy, change in entropy, right? And you usually, if you're going to do this calculation, you have to have a constant temperature, right? And so the only times that heat flows in at a constant temperature is when you have a phase change, right? So really, if you look at you start with a solid, then you melt the solid, then you heat up the liquid, then you boil the liquid, then you heat the gas, this sort of thing, right? In these little things here, right, that heat flow is actually at a constant temperature. Now, by the way, if the temperature changes in this case, you have to do calculus, right? We have to do a little, and I don't think they're going to throw that at you, right? Okay. But this is heat flow. And then remember, if this is positive, then the entropy is increasing, right? And this makes sense. If you think about this, right, if we go from a solid to a liquid in terms of disorder, right, or in terms of just possible states, right, that's what this guy is here. If they're locked in a crystalline solid versus they're free to move, there's more possible states for those things to be in. If they're locked solid cheek and jowl, right, you just picture some crystalline solid like this where there's an orderly arrangement. There aren't very many possible states for it to be in, and that's what this omega is. Right? The possible states are limited. It's just this guy's always going to be my neighbor. He's never going to be next to this guy, et cetera, right? Okay. And so a liquid is more entropic than a solid, right? And likewise, a gas is more entropic than a liquid, right? In a liquid, at least the particles are right up against each other, right? In a gas, they're ping-ponging around inside this space, hardly even saying hi to each other, kind of a thing, right? So these are entropy calculations, right? This guy is a new one for the 2025 curriculum. So it's Boltzmann's constant times. I actually learned this. I took thermal physics largely because the professor wanted to teach it, right? So it's literally calculating it. It's the number of possible states, right? And that's the sort of stuff you did in probability, in maths class, right? You talked about the possible what are the odds of this happening? Well, you just map out all of the possible states, right, that you could have. That's literally what that omega is there. Okay, I don't know how they're going to work that into a problem, but we'll see. Okay, this is to figure out change of U in these cycles. This is an adiabatic process, right? Okay, so in an isothermal process, where are we here? Isothermal, you can go PV equals PV, right? Because the denominator is NT, right? But N stays constant, T stays constant, right? So isothermal, that's what we're going to do. For adiabatic, because the temperature can change, right? If I push that piston down, I'm adding energy to the system, right? And the temperature will rise. And if I push the piston up, the temperature will drop. This is how freezers and heat pumps work, right? So for adiabatic processes, you've got PV to the 5/3 equals PV to the 5/3. Okay. So that's sort of the cycle and the process stuff that we've got. And then we've got Carnot cycle stuff, right? Let me erase here. So these guys, this is just efficiency, right? So it's work, right? Work output over energy input. It's the same formula that we've had before, right? Okay, it's output over input, right? And then if you have this perfect Carnot cycle, right, then you get the Carnot efficiency, right? And Sadie Carnot proved that this is the most efficient that two different temperatures can create, right? And it's 1 minus the cold temperature, of course, in kelvins, right, over the hot temperature. Right. Okay. So what happens is, and we can draw like we can draw a little diagram here. Right? We've got a high temperature reservoir, right? We've got a low temperature reservoir. We draw these things. These are called Sankey diagrams, right? Okay, and so heat flows in. Okay, maybe this thing is 80% efficient or something. So here's work. This is our QC. This is our all the way across here. And they don't have this formula in there, but basically it's kind of like this one, only it's different, right? Okay, so it's the QH, if heat flows into the thing, right, it's going to equal what's wasted plus any work that you do, right? So maybe this thing is 80% efficient, right? If 100 joules flows in, we waste 80 joules and we get 20 joules of work. This thing is 20% efficient. And you guys, I assume you guys have done some problems like this. So there it is, right? And so something that has a Carnot efficiency, you can actually calculate it like that. And then just remember that the heat engine cannot be more efficient than the Carnot efficiency. I didn't actually come up with that pun. Some student did. What was his name? Harrison. Rick? No, geez. Anyway, class of 1994. He put that on the test. He said, I calculate the Carnot efficiency. And he said, I'm sorry, I cannot do that. Silly kid. Anyway, that is sort of, I don't know, thermodynamics, sort of.